All right, Calc students, Mr. Antonucci here, and in this video, we're going to have an introductory lesson on related rates. When we talk about related rates begins with the understanding that we treat both variables x and y as functions of time, and we differentiate with respect to t. Now, since we're treating x and y as functions of t, we're going to differentiate using implicit differentiation. It always helps to have a bunch of quick examples to show you how this works. We're going to treat x and y here as functions of t and differentiate each of them with respect to t. So this one, differentiate with respect to t, is going to be dy dt. And you want to use the Leibniz notation here. This, if we differentiate it with respect to t, you would have to use the chain rule, 2y times dy dt. And same thing with the y cubed. If we differentiate this with respect to t, use the chain rule with implicit differentiation. It'd be 3y squared times dy dt. Now, if we switch to x, remember, x is treated in related rate problems as a function of t. So we're going to do the same thing here. The derivative of x is going to be noted as dx dt. The derivative of x squared is going to be 2x times dx dt. We got to use that implicit differentiation. And then if you had x to the sixth, if you're differentiating it with respect to t, it's going to be 6x to the fifth times dx dt. Now let's look at a couple more equations here. If we want to differentiate both of these with respect to t, well, I would need to differentiate with respect to t both sides of this equation, and y is going to be dy dt. X cubed we know is 3x squared times dx dt. And the derivative of the constant 6 with respect to t is still going to be 0 because it's a constant. Now, a question that may come up is, how do you know when you have to differentiate with respect to t and use the related rates situation? Well, the context of the problem will let you know, and we'll look at some examples of that. Also, you may have some problems where it explicitly says differentiate with respect to t. This second one here, the derivative of y squared is going to be 2y dy dt. And then the derivative of 4 cosine x is going to be negative 4 sine x times dx dt. The derivative of the constant 1 is just 0. Now, we could solve this for dy dt if we wanted to, or we could solve it for dx dt. Depending on what the problem is also asking you to do, will determine what you do from here. For this problem, this is all we needed to do. In this kind of problem, it tells us that x and y are differentiable functions of t, so we know we are going to have to differentiate with respect to t and use implicit differentiation. So if we want to find the value of dx dt when x is 1, if dy dt is 3, and the equation is y equals x squared plus 3, first thing we would do is differentiate everything with respect to t. So the derivative of y with respect to t is just dy dt. The derivative of x squared would be 2x times dx dt. And the derivative of the constant 3 would be 0. If we want to find what dx dt is when x is 1 and dy dt is 3, you could either solve the equation for dx dt first and then plug the values in, or plug the values in and solve for dx dt. I often will plug the values in first because then that simplifies a lot of things. So for example, dy dt is going to be 3 and x is going to be 1. So dx dt is just going to be 3/2. Many times you're going to have a situation in which there's a shape or some kind of situation that can be drawn out. In this case, a rectangle's length and width are changing as time t passes. That is telling you that the length and width are functions of time. We want to write an equation that relates how the perimeter is changing over time, and then we're going to do the same thing with the area is changing over time. Well, we know that perimeter is equal to 2L plus 2 W, if this is the length and the width. If we want to know how the perimeter is changing over time, we would have to take the derivative with respect to t. The derivative of 2L with respect to t would just be 2 dl dt, and W would be 2W dw dt. And that's it. They didn't tell us any other values to plug in, so it just wants the equation there. If we do area, area is length times width. So when we differentiate with respect to t, the derivative of a with respect to t is just dA dt. Then we'd have to use the product rule here because L and W are both considered functions, and we're differentiating with respect to t. So the derivative of L is dL dt. So that's the derivative of the first times the second, plus the first times the derivative of the second, which since it's just W would be dW dt. Here's just another one with a circle. It says the circle's radius is changing as time t passes. Again, this is implying that the radius of the circle is a function of time. So we want to write an equation that relates how the area is changing over time. So the area function, so area equals pi r squared, is the equation that relates the area and the radius, but we want to know how that is changing over time. So we would differentiate this dA dt equals pi times r squared. The derivative of the r squared would be 2 pi r times dr dt. And that's all the further we would need to go there. If we do the same thing with the circumference, we need the equation that relates the circumference and the radius. So circumference equals 2 pi r. Then the rate of change of the circumference is equal to 2 pi times dr dt. One other thing I want to point out is that this area equation, if we rewrote it as 2 pi dr dt times r, I just rearranged the multiplication. Notice that the 2 pi dr dt is the same as the equation for the circumference. So I could rewrite this as dA dt equals the rate of change of the circumference times r. I've seen AP style questions where you had to know this relationship or understand it in order to solve the problem. A couple more things is it's important to be able to translate a verbal statement into a mathematical model with related rates. So for example, the verbal statement, the velocity of a car after traveling 1 hour is 50 miles per hour. So in the mathematical model, we could say that x equals the distance in miles, and the velocity after traveling 1 hour is 50 miles per hour. So that would be dx dt equals 50 miles per hour when t equals 1. So that's the information that's given in that verbal statement. The next one, water is pumped into a swimming pool at a rate of 10 cubic meters per hour. The function involved is the volume. So V would equal the volume of water in the pool. And then the rate of 10 cubic meters per hour, that would be dV dt equals 10 cubic meters per hour. The next one, a gear is revolving at a rate of 25 revolutions per minute. So since the gear is rotating, we have an angle of rotation or angle of revolution. We'll call that fatal. And we often will use radians. So it's assumed that this is going to be radians. And then 25 revolutions per minute, that would be the rate of change of the angle. So d theta dt is equal to, be careful here, it's 25 times 2 pi radians per minute. Because to spin the whole way around would be 2 pi. So that's your factor. Population of bacteria is decreasing at a rate of 2,000 per hour. So P would equal the population of bacteria. And then dP dt would equal negative 2,000 bacteria per hour. So be careful. I highlighted the word decreasing in red because that implies that the rate is negative, even though they stated the number as positive 2,000. Since you have that qualifier there of decreasing, that's going to introduce a negative. Now, I just want to give you some quick steps, some guidelines for how to solve related rate problems. First, you want to identify your knowns and unknowns. Then you want to sketch and label a diagram if that's necessary. Then you want to write an equation that relates the quantities involved. Then third, you want to differentiate both sides with respect to t, or time. And remember, you're using implicit differentiation here. Then you plug in your known values, solve for your unknown, and be sure to include any units if there are units involved. All right, I got one quick ACE-P style question for you. Let x and y be functions of time. There, they said it right there. Now you know it's a related rate problem, such that the sum of x and y is constant. Right there, they are telling you the equation in a verbal statement that relates the quantities involved. So I know that x plus y is going to equal some constant. We'll call it k, because I see k down here in the multiple choice answers. Which of the following equations describes the relationship between the rate of change of x with respect to time t and the rate of change of y with respect to time? So we want to differentiate with respect to t. So dx dt plus dy dt equals 0. Remember, k is a constant, so its rate of change is 0 no matter what you're differentiating it with respect to. Now, none of these have dx dt plus dy dt equals 0. C is incorrect, even though it does have dx dt plus dy dt. It has dk dt, where k is a function of t, and that's wrong. K is understood to be a constant. So that eliminates this one as well. Now, the two that are left, notice they solved both of them for dx dt. If we solve this equation for dx dt, we would have to subtract dy dt to the other side, choice B. Well, that's it, guys, for Intro to Related Rates. Hope that was helpful to you. Let me know in the comments what you like best about this video. Make sure you subscribe to the channel if you are not, and hit that like button. It helps out. Take care.